Hi, I'm Yifei, and all right, let's get back to the ground. So my topic is roaming free in the VR world with MP2. And this is a collaboration of UCLA, Alibaba Cloud, UC Merced, Uber, and University of Michigan. So the first question you may be asking is, what's free roaming VR? It's basically people standing, multiple players standing in the same physical space, but their action, their movement, their location are mapped to a virtually rendered space. And you can imagine it's useful for gaming, for virtual tourism, for training, for education, and more. And specifically, you don't want to carry a very heavy renderer with a GPU on your back or on your headset. So wireless streaming is usually the preferred option due to the weight, battery, and temperature consideration of your headset. But free roaming VR streaming actually requires mobility, scalability, and efficiency. Mobility means your streaming system at least needs to allow user to roam across multiple access points. A single access point or a cell, a base station, is not sufficient. And scalability means you need to support up to tens of users so that they can interact in the same virtual space. And again, a single AP may not be sufficient to carry their aggregated throughput. And efficiency means your system needs to meet the minimum bandwidth and latency requirements for the VR application. Otherwise, people will get dizzy. So naturally, Wi-Fi becomes a go-to choice, primarily due to the cost and throughput advantage compared to some other options like private 5G or other wireless technologies. And it's also the simplest one, so we start with this one. But again, the next question is, does existing Wi-Fi streaming work well for free roaming VR? We did a case study with the Steam VR platform and ALVR, which is a popular open source VR streaming solution, and Xlink, which is a state-of-the-art multipath transport protocol that actually help with handover between Wi-Fi APs. And also we use a high-end gaming Wi-Fi router. But the outcome turns out to be, firstly, we've seen high handover latency. Even we actually see a packet gap of up to 50 milliseconds on the left compared to the desired migration on the right, which should ideally be seamless. And also, even with a state-of-the-art multipath protocol, it did mitigate the latency spikes, but it ignored the fact that Wi-Fi radios needs time to wake up, so that we still have this 50 millisecond packet gap upon handover. And the second problem is we've seen unstable bitrate. So we already know that bitrate adaptation under a dynamic link is already challenging. And it becomes more complex under multipath transport because it creates a double control loop problem. The control mechanisms interfere with each other. And what makes it worse is that the streams will compete for resources. In this case, 4 streams compete with each other under the same AP, and each running its own ABR algorithm, adapting the bitrate to the link. And the bitrate just fluctuates and never coming to an convergence. And third problem is imbalance the loads. So we've seen that existing Wi-Fi clients tend to select the AP with the best signal quality regardless of congestion. So in the left case, there may be imbalance. And if ideally the load can be balanced, the tail latency can be greatly reduced. And we found that the root problem is the existing Wi-Fi streaming system lacks a global view of load distribution. So it's not possible actually for them to reach a balanced load. To solve the previous challenges, our answer is MP2, multipass for multiplayer. So in short, it is a centralized overlay system that has a global view of the entire stack, and it coordinates the link path bitrate decision. These are cross-layer decisions. And it coordinates the decisions across users on different APs. So before really diving into the details, we present some observations. The first thing is on this specific task, we find that centralization still beats decentralization. Because centralization allows you to coordinate decisions across, firstly, users, and secondly, different network layer, from the link layer to the transport layer to the application layer. And also, secondly, single Wi-Fi interface is not sufficient. With a single Wi-Fi interface, even with fast handover techniques, we are still seeing 100 millisecond level network outage upon a handover. And also interference, congestion, and signal degradation, these all leads to reliability issue for a single Wi-Fi interface. And thirdly, we find that user space, if you really want to deploy a streaming system, it's better to make it in the user space. Any OS level modification and special hardware will slow down your deployment. And also, a user space implementation is easier for adapting to new evolving wireless technologies, say newer version of Wi-Fi. So, okay, here's a system overview. So with any kind of multiplayer Wi-Fi VR streaming system, you need to firstly have the VR server, VR rendering servers running the VR application and the streaming applications. And you also have a set of headsets and a set of APs in the middle that carries the throughput. So what MP2 introduced here is firstly a data plane with the MP2 tunnel client and tunnel server. So they are built on top of multipass quick protocols and leveraging the two Wi-Fi interfaces on each headset. And the main goal is to mask the complexity of path and AP management and packet delivery. So it can route the VR traffic according to the decisions from the control plane. So we only need to focus on which stream need to go through which AP under the current circumstance. And then we have the control plane, the controller. So the MP2 controller collects global cross-layer information, including the Wi-Fi's physical layer info, primarily RSSI in our implementation, and VR application data, primarily frame size distribution. And with this information, the controller orchestrates cross-layer information to optimize the global QoE. And the decisions include the AP association, the path at the link layer, and the path selection at the transport layer, and the bitrate guidance at the application layer, which controls the streaming server encoder. And also, to ensure smooth migration of link from one AP to another, it also coordinates stream for a seamless migration. So, and the best thing is everything is in the user space. We do not need all of the tunnel client, tunnel server, and the controller are standalone applications that can be run on any device. And we do not need modification to the kernel, and the whole system can be implemented with low-cost commercial Wi-Fi hardware. Okay, we will firstly introduce the coordinated seamless migration part, because this is actually a combination of tricks. The first trick is path warm-up. Before migrations, since MP2 schedules the migration, so it can send a small probing traffic in advance over the target link to keep the Wi-Fi radio hardware active, not radioactive. And the second trick is redundant transmission. But during transmission, MP2 adopts a short transient full redundant transmission on both passes, on both the old AP and the new AP to switch to, so to minimize the packet loss and latency. And the third trick is the bitrate guidance. So without bitrate guidance, we've seen that after migrations, the ABR algorithms can usually take up to or more than 10 seconds to converge. And what MP2 does is it proactively enforces a maximum bitrate cap for all users on that involved AP. So it can achieve faster convergence, and it's nice that ABR can continue to adapt so that MP2 can coexist with other non-VR traffic that are not considered in the decision phase. So with the guarantee of a seamless migration, we formulate the control problem. The inputs are basically RSSI from the clients and frame statistics from the streaming servers. And the outputs are AP selection, which means which AP or path should each stream be routed through. This also implies which AP should each Wi-Fi interface be associated with. And the second thing is bitrate guidance. Which bitrate should each stream run at? And the optimization goal is listed here. This is nothing special, but it's just a heuristic combination of bitrate and lag rate of each stream. But the tricky part is to get the lag rate or to compute the lag rate, you need to predict the tail latency for each frame. But clearly, we don't have a closed form prediction for tail latency right now. And without this, the tail latency has to be obtained from a fine-grained simulation with recorded video traces and counting the delayed frames, which is very inefficient. And also, the search space is intractable. It grows exponentially as the number of users grows. So with 4 APs, 12 users, and 10 bitrate levels to search, and if suppose you need 0.1 second to run a single simulation, you'll need 1.7 times 10 to the 18th seconds to obtain a single decision in a single round, which is completely not acceptable. So firstly, to give a closed form prediction of the tail latency, the controller provides a frame size modeling. So starting from a simple case, suppose that k streams compete for the same AP. In the worst case, the frames from all streams collide. And the worst case latency would be the aggregation of the frame size from each stream divided by the link rate. And we found that if the sizes of every stream, if the frame sizes of every stream all follow the Gaussian distribution, their aggregation is still Gaussian. So we can easily obtain a closed form worst case tail latency from this assumption. But in practice, we have mixed the frame size. But fortunately, we can use the Gaussian mixture modeling. And we find that it can closely track and mix the distribution, mix the frame size distribution from a real VR stream. And under this modeling, all the above still holds. So we can get a closed form worst case tail latency for a VR stream with mixed frame types. Okay, the second problem is the search space. To make the search space somehow tractable, we do pruning and partitioning. We prune, when searching in the search space, we prune the links. We skip the bottom P% of poor links based on the collected RSSI. And we also do location-based partitioning, where we partition the user into location-based cells, and we optimize arrangement locally within each cell. And with bounded cell size, we can guarantee that the search space grows linearly with the user count. So with all these, we reduce the compute for one decision down to less than 1 second for a setup of 48 users and 16 APs. Okay, we move on to the implementation. So we did implement our platform with a set of GPU users running on Linux PC, and with Steam VR as the rendering engine, and the AR VR server as the streaming server. And one problem for the headset is currently no commercial headset supports multiple Wi-Fi interfaces. So we have to do it on a Linux PC. And to run the same VR streaming client, we use the Monado, which is a cross-platform XR runtime that can be run on Linux. And we run the same AR VR client. And for the MP2 related components, we have the controller that can be run on any one of the servers, the tunnel server that can be run on any one of the servers, and the tunnel client needs to be run on every headset. And the good thing is all of them are portable applications for Linux PC. And yeah. And we did our evaluation on seamless migration in the real world. And it's actually an ablation study. We can see that both the redundant transmission and the warm-up contribute significantly to the reduction of tail latency. And we also see that the bitrate cap actually can smoothen the tail latency, smoothen the bitrate and tail latency by a lot. And also, we did a large-scale emulation using Mininet Wi-Fi in a 16AB48 client setup. And compared to other potential protocols that can do some sort of semi-local optimization, like the mostly MP-Quick, different flavor of MP-Quick, MP2 performs the best. For the detailed numbers, please refer to our paper. And we also did a user study with a trace-driven user study with the network traces recorded from our previous experiment and real headset. And we've seen that the perceptual quality of experience is higher for MP2. And MP2 consistently performs the baseline, outperforms the baseline. And even for the rare cases where MP2 is not better than the baseline, it's almost a tie. So as a summary, we've seen that handover latency, bitrate fluctuation, and imbalanced loads are 3 roadblocks to multiplayer free roaming VR. And to solve this, MP2 introduces a user-space centralized overlay system that has a global view of the entire stack and coordinates cross-layer, cross-user decision. And yes, the only hardware gap is the second Wi-Fi interface on the headset. And that's absolutely doable because typically that only costs several to $10 nowadays. So thank you for listening to my talk. Welcome any questions?